All right, before we get started, anybody have any questions about anything? All right, so I believe section 2.2 is due tonight. We're going to finish 2.3, that'll be due on Monday night. And then 2.3 is basically, that's the end of the coverage for the first test. So we'll get a little bit deeper on today and Monday, but not too much further. I sent out a survey for when I might hold a review session, or basically an extra office hour this coming week. Thank you to those of you who filled it out. If you're interested in going or interested in me having one, go ahead and fill it out if you haven't. But it'll be next week sometime. I did. So I sent a mass email through Canvas. So yeah, if you have an email you check more regularly than your ASU email, then you probably didn't see it, but it went to your official ASU email. All right. So we did a lot of stuff with differentiation rules last time. Now we're going to derive some for the trig functions. So this graph right here is one period of the function f of x equals sine of x. And we're going to use this to find out what the derivative is. So let's do this. Thinking about what the derivative of a function tells us, and I'm showing you the function sine of x, can we say anything about what the derivative is going to be equal to? How come we can say that? Slope of the curve is 0. Similar situation to 3 pi over 2. How about 0? Let's just stick with 0. So I got to vote for positive 1. We okay with that? I don't know if we can say 1, but we can certainly say it's positive, right? I'm going to go ahead and spoil it for you to tell you it's 1. And by the same logic, and especially if we know how trig functions work, they just repeat every 2 pi. Derivative at 2 pi is going to be 1 as well. What about at pi? -1? We okay with those 5 points? Yeah, lost this point. So if we connect those, does this look familiar to you? What is it? So that derivative is cosine of x. So the derivative of sine of x is cosine. Any questions here? All right, now let's start with cosine. Why did you go back? Yeah, of course. Oh, we should not have graphed that original one in red. So this is f of x. This is f. Now starting with cosine, we want to find that derivative. So what are some points I can plot for the derivative straight away? Okay. How about the ends of this interval? 0 and 2 pi. For both? Yeah, let me stop there. Anybody have anything else to add? We agree with this? Questions about why those 5 points happened? Go ahead. So I'll throw it back to the class. So let's just start with the one on the far left. Why did I plot this point 0, 0 here based on the graph of cosine x? So yeah, if I were to make a tangent line at this point here, that would have a slope of 0. By the same logic, this slope would be I mean, the best you can see is that slope is negative. I am telling you that it happens to be -1. But yeah, really, we're just thinking about what the derivative tells us. Slope of the curve, slope of the tangent line. Similar ideas there, but yeah, basically we're just, to find the derivative, we're figuring out what the slope of the tangent line is. So from those 5 points, if I graph them, we recognize this thing. Yeah, I got to vote for cosecant. I got to vote for negative sine x. Sounds like negative sine x is getting some support now. That one's a little harder to see. I think, we all know what sine of x looks like. Recognize that it looks familiar or somehow similar to that, but it's the opposite, reflected over the x-axis. Cosecant looks quite a bit different. I don't want to muddy the waters too much by graphing it, but the big difference for like cosecant and secant, those are not continuous everywhere. Those have discontinuities every so often. All right, so got derivatives of sine and cosine now. Any questions on either one of those? Okay. So now that you know them, in the last day and a half or so, we should be able to get a derivative. This function, if y equals 3 sine theta plus 4 cosine theta, it's down to one term at a time. 3 sine theta, what's the derivative of 3 sine theta with respect to theta? Or should we just ask what the derivative of sine theta is? Cosine theta, right? So maybe I'll break it down one more time like this. This derivative, I can break it down like this. 3 times the derivative with respect to theta, sine theta, plus 4 times the derivative of cosine theta. So what's this first term become when all is said and done? Cosine theta. And how about this other one? And it's 4 sine theta. And so I want to highlight something here. I'll call this dy d theta as well. Yes. Yeah, there's no independent variable x this time. All right. So we've talked about speed in the past. I think the very first thing we talked about as a motivating example was the idea of speed. So let's kind of get back into that. So I'm giving you some particles just moving around in one direction. And its distance from some starting point, its position is given by this function. Position is measured in s, time is measured by, or given by t. So the first thing I want to do is this. I want to find the velocity at time t. So s is the position. So if we think about how position and velocity, those ideas are related to each other. Velocity is a rate of change of position, right? So if I have a function that gives you a position and I want to get a function that gives you the rate of change of position, what do I need to do? Find the slope, and what's that process called? What's that? I need to find the derivative. So at its core, what a derivative is, the derivative really is it's a function that tells you the instantaneous rate of change of some other function for whatever value of the independent variable I want to use. So if I want to find velocity here, I'll call it vt. That's really the same as finding s prime of t. Now we just need to take the derivative. What is the derivative of this function s? Vote for root 2 squared minus 12t plus 9. Agreements, disagreements, questions? All right, I agree with this. This is the velocity at time t. This is the velocity for any time t. Now I want to know what the velocity is when time equals 4 seconds. So now what should I do? Plug 4 into what for the derivative? There you go. So yeah. And the reason I'm bringing it up is sometimes you might know what the rate of change is, and you want to solve for some other quantity. I don't want v of t in general. I want v of 4 in particular. So 3 times 4 squared minus 12 times 4 plus 9. So 3 times 16, 48. Is that just 9? Yeah. Yep. All right. The final question I want to ask is, when is the particle at rest? What does that mean? So I've got a lot of things there. No, it's like not exactly calling for hands or anything. I heard the word zero. I heard the phrase rate of change. So what's that zero referring to? What do I need to look at? How fast the particle's moving. So you want its speed to be zero then. Okay. So in this case, how can I answer this question given the mathematical information I have? I need to set the derivative equal to 0. So I need v of t to equal 0, which means this is true. 3t squared minus 12t plus 9 equals 0. Divide the whole thing by 3 and get t squared minus 4t plus 3 equals 0. Does this thing factor? So those times are going to be 1 second and 3 seconds. Oh, ahead of myself. Number 3, then the letter S. Rest. So this idea here, and let's unpack it a little bit. I said that when t equals 1 second and 3 seconds, the particle's at rest. It's not moving. But for how long is it going to be at rest? It's just for no time at all. And contradictory, but they're not. It does come to rest, but it's only for an instant. You can't measure that. You can't measure that amount of time in a positive way. So that was kind of a tangent to this, but yeah, this phrase right here, at rest, means, and I'll just say in general, rate of change equals 0 at that instant. Did I answer your question? Basically the fact that I have this equal to 0. I can, yeah, there was a non-zero number over there. Anything else? Go ahead. That is, well, there's, the short answer is by definition. So I'll answer this mathematically. If I have a function, I can find another. Physically speaking, basically the physical and the mathematical way those two things are related. Go ahead. Yeah, so let's just unpack the last one here. So if I have a function called v of t, how many variables am I implying there? Okay, I got to vote for one. What variable is that? Okay, v, that's the velocity. And I'll measure that in meters per second. Is that the only variable that I'm implying with the notation v of t? Yeah, so the v of t, I mean function notation. So yes, function notation basically says I am giving you a value v, but that value v is governed somehow by this value t, which is time. In seconds. So for the first one, that middle bullet, what's the velocity at time equals 4 seconds? I am fixing a moment in time, and I want to learn about velocity. When I ask when the particle's at rest, I'm saying, okay, I want the velocity to be, I'm fixing the velocity, and I want to figure out what values of time deliver that velocity that I care about. So essentially, I mean, basically, you know you're going to be plugging in something for some other variable in both those cases, but you need to be careful about what is being asked for. All right, let's go into a little more detail here. When is the particle moving forward? So I'll go ahead and write down the velocity again. We already have it. So if I ask a question like that, when's the particle moving forward? How can I figure that out? Using my mathematical information. All right. So let's be real specific here since we're kind of getting into a represented scenario. You say when what equals 0. Okay. So Vt equals 0 when t equals 1 and 3. Is that right? Okay. So I know when the particle is not moving. So presumably it's going to be moving forward. So it's not moving forward at either one of those times, right? So let me ask this: when might it be moving forward? When the derivative is positive. So that's really what we're looking at. That implies forward. motion. So I guess we can ask, how can we find out when that derivative is positive? Yeah, that's what I was getting at. Here's one thing I think when we solve equations, the thing we're really after is what the solutions are. But the other really important thing when you solve an equation so in this case, I know the velocity is equal to 0 when t is equal to 1 second, 3 seconds, and the part that we kind of lose sight of is nowhere else. And the reason I say that's important is because I really only have to look at these three intervals between 1 and 3, from 3 to infinity, and what other interval? So I'm glad someone said 0 to 1. Why is it 0 to 1? Well, the derivative it could be positive for like negative values of time, but we kind of assume in this situation that negative values of time are meaningless. Because if t equals 0 is when I begin observing this thing, it doesn't really make a lot of sense how do I know what was happening before that? I wasn't even observing. So these are the three intervals I'm looking at. So what's a good test value to use between 0 and 1? And actually, you know what? Can I use 0? Yeah, there's no reason I can't use 0. V prime of 0 is equal to 9, right? What's a good test value between these two? Oh, no. Slide. What's a good test value between 1 and 3? Yeah. What is the velocity at 2? Three times 4 minus, bad. 12 minus 24 should be -3, which is less than 0, so that's not true. And I'll just do v prime of 10 for fun. We would suspect this one's going to be positive, but let's make sure. 3 times 100. Is it 99? That's good. 300 minus. I think 189 is that. Am I wrong? Right. So basically, it's moving forward at when t is somewhere inside this interval between 0 and 1, united with 3 to infinity. Go ahead. There's one next to 10. But I have to choose 10? No, that's the bottom line. You can just it has to be on the interval. All right, next. All right, now I got another word to throw at you. Find the acceleration when t equals 4 seconds. Right, so, and that's another kind of definition thing. The idea of position, the rate of change of position is this idea called velocity. How is acceleration related to velocity? Much in the same way. The acceleration is the instantaneous rate of change of velocity. So if I want to find acceleration, call it a of t, which is pretty common. I want to find v prime of t, which is the same as s double prime of t. And really the hard part of this question is you knowing that that is how acceleration is related to the other concepts I've thrown at you. So what is the second derivative of s? 16 minus 12. Which really, when we find second derivatives, we are really finding the first derivative of a first derivative. Got to take them in steps. So now that I have the acceleration, that's the acceleration function. What I really want is the acceleration at a specific instant. So what do I need to do? Or what? There you go. Yeah. So acceleration is 6 times 4 minus 12, which is 12. You know the units on this thing? Meters per second. I'm assuming those of you getting velocity acceleration. Get a handle on for what we're going to be doing. Do you have a question? How did we get 16 minus 12? Yeah, so really, I gave you one function. We could go further, but yeah, we just basically when you're finding a second derivative, yes, it is the second derivative, but really mechanically you're taking a first derivative of some other first derivative. Got to do them in steps. The third derivative is called jerk, and I've never thought about it. I've never really dealt with it outside of the classroom. But it exists. People measure it. My background's in electrical engineering, so it didn't really make sense for me to look too deeply into it, but I know people do. Any other questions here? So that was 2.3. Let's get into 2.4 for a bit. And I do want to make sure, so this concludes the coverage of exam 1 stuff. The stuff we're about to do, you're responsible for, but it'll be later on. All right, so we're going to talk about the product and quotient rules now. And I'm just curious, has anyone seen these guys before? Yeah. The number of hands is getting smaller. All right, so we're not going to take derivatives of all 4 of these things, but right now I'm going to ask, based on the tools that I have, which of these can we take a derivative of right now? Yeah, I got to vote for just the first one. Do we agree that the first one can be done with things we know now? Yeah. We're saying no to the second one? I'm going to say yes, you can do the second one. No, you can do it correctly. Oh, I don't think it'd be that long. How long would that take you? So I think realizing that it can be rewritten into something a little more digestible, that can be done. Did I hear you vote for yes? I have not given you the weapons to do this one yet. And this bottom one, can I divide by x plus 3 there? Not in a way that's going to get you to an easy derivative. So we can do things like the top two. The first one, I'll jump to right away. Like a lot of you probably did that in your head. I could ask you for it right now. Second one, You might even be able to do the rewrite in your head, but maybe you didn't realize that you could rewrite it like that. So what we're going to be talking about now is how to deal with things that look like each functions either multiply, it's like two smaller functions multiplied together, or divided by each other. So a few of you have seen the product rule, but let's figure it out. So I want to find, so I'm saying capital H of X equal to this product of two other differentiable functions, and I want to find a derivative. So how do I find this derivative, H prime of X? Not based on any, just go back to the fundamentals. How do we find derivatives? Or where do they all come from? Yep, the limit, we're going to just go, oh, not F, capital H of X plus H minus capital H of X over H. But now let's put in those other pieces. This is the same as F of X plus H, G of X plus H, minus F of X, G of X, all over H, right? Okay, so now I still have no idea how I'm going to get to that limit. So what I'm going to do, I'm going to bring in this kind of weird thing that might not make any sense at first, but it will. F of X plus H times G of X plus H minus F of X plus H, G of X, plus F of X plus H, G of X, minus F of X, G of X. And I will pause there. Try so badly to draw a straight line. Good enough. Are we okay that that's equal to the step that came before it? Yeah, really all I did. So that those two middle terms add together to zero. So I really haven't done anything illegal. But now that I have this, I'm going to split this limit up into two different things. The limit as not X, which approaches zero, of F of X plus H, G of X plus H, minus F of X plus H, G of X, all over H. And then the rest of it is going to be F of X plus H, G of X, minus F of X, G of X, over H. So still really haven't made any, I haven't made any substantial changes. I'm not allowed to. All I'm doing is just moving things around, breaking the fractions up. Now, with each one of those, is there something I can factor out of the numerators in each of these? Yeah, so in the first one, I can factor in F of X plus H. And that leaves G of X plus H minus G of X all over H. In fact, I want to write this differently than that. I want to really keep those apart. And same thing over here. If I can factor out a G of X here, I'm left with F of X plus H minus F of X all over H. All right. A lot of stuff, but are we okay with it? Sebastian, your question? So now I have two different pairs of, like, I have this limit on the left is the limit of one thing, basically of one function times another, right? But if those individual limits exist, then I can just take the limit of one at a time, right? So let's talk about the limit of x, the limit as h approaches 0 of f of x plus h. As h gets really, really small, that's just going to go towards f of x. This thing here in the bracket, g of x plus h minus g of x all over h, what does that look like? That's the derivative of what? Of what function? Yeah, g of x, right? So if I take that limit, that all comes down to f of x times the derivative of g. On the other side, that g of x is easy. There's no h in there. That's going to stay g of x. What's that second term look like? That's the derivative of what? Prime of x. So, and I show you this proof just to show you that this is where the product rule comes from. I'm guessing that most of you who have seen it have probably not seen exactly where it comes from, but this is the product rule. H prime of x, and I'll just put it in, the full thing here is going to be equal to f of x g prime of x. Very nice looking symmetrical thing. Actually, I'll rewrite it. It's probably the most common way to show it. Don't change the order of f and g, just change the order of it. Just change this when you're differentiating. What do you think? Does the order matter? Why doesn't the order not matter? It's multiplication and addition. Those things both commute. So yeah, it does not matter which one you differentiate first. As long as you don't do like f of x times g of x, you do have to multiply the correct components together. Any questions on this before we use it a couple times? Go ahead. Yeah. Assume f and g are differentiable. And the reason you have to assume that is because, well, I can't find the derivative of functions. Derivatives don't exist. So I'm going to assume they're differentiable. But thinking back to last time, if a function is differentiable, it is also. Anything else? Right. So let's use it. We got this function x squared sine of x. This is one of the ones we just said we couldn't do. No longer true. Well, let's break it down. Let's break it down into two smaller functions called g of x and h of x. What's a good logical choice to make for what those functions are? So yeah, call one of them x squared. Call one of them sine of x. Since this is our first one, I'll go ahead and do a template here. You want to find the derivative of g or h first? Sounds good. They're just names. So the rule I just gave you, this time I called the parent function. All right. So now we can start filling in these. I guess we can just make all the ingredients up here. If g of x is x squared, what is g prime of x? 2x. And h prime of x is sine of x. And now I can basically, I'm just filling in the blanks down here. So I get 2x sine x plus squared cosine x. And the reason subtle but very important. Yeah, so on the last slide, I didn't have words. And I'll keep emphasizing for product rule because when we do quotient rule, that won't be true anymore. I have to really respect the order. Any more questions on how we got these derivatives? That is it. I mean, you can re-express it, factor some things, and that's it. That's a good. Anybody else? Okay. Can I do one more? I believe so. Any suggestions how to start? A and B are constants, by the way. Okay, so it sounds like you are proposing this composition. Is that the only way this can be done? You distribute. So A radical t plus bt to what power? So here's the temptation that I want to point out to you is just because you can use the product rule doesn't mean you have to. And really, I'm going to make us go through the product rule because we're practicing it, but you're going to come across situations where just because it looks like it's the way to go doesn't mean it's A, doesn't mean it's the only way to go. B, doesn't mean it's the best way to go. In fact, on that first slide, I showed you one where the quotient rule could definitely be used, but it would take so much longer than just simplifying first. For this one, let's go ahead and use the product rule. If I want to find f prime of t, let's be consistent with the first way I showed it to you. I have g of t, h prime of t. Even if I didn't, this will still work. So g of t is just radical t. What is h prime of t? Gonna vote for just B? We okay with that? And I really want to stop here because I think derivatives, it can be a little tricky when, especially when you kind of have this assumption that, oh, letters are variables. And really that's not always true. So are we okay with the fact that the derivative of A is 0? The derivative of bt is just b. Okay, so that's the first term. What is g prime? And just to kind of show why that's true, that's the same as you doing this. Easier to use the power rule if you're actually expressing things as powers. And h of t is a plus bt. Do a little simplifying, but not too much. Well, yes. By rewriting. So that 1/2, basically, if I were to put that all into one fraction, t to the negative 1/2 times a plus b. I have to say, have a good weekend. All right, so yeah, if you haven't responded to that survey yet, please do. We'll get that figured out, or if you want to review anything at all between now and the test, please let me know.